Okay, in this lecture we're going to continue our section 3.2 material on the theory of second-order linear differential equations. And this next part of our section we're going to introduce a result known as the superposition principle, which will tell us information about how to construct the general solution of a second-order linear equation. And it sort of helps justify what we were doing in section 3.1. It tells us why the general solution has the form that we looked at in that section. So let's start by taking a look at this theorem. This is theorem 3.2.2 from your textbook. It's called the Superposition Principle. And it says if y1 and y2 are two solutions of the differential equation y double prime plus p of t y prime plus q of t times y equals 0, so a homogeneous second-order linear equation, then the linear combination of those two solutions, something like c1y1 plus c2y2, is also a solution for any values of the constants c1 and c2. That is, any linear combination of two solutions will also be a solution. And this is an important result for our theory in chapter 3, so I think it's worthwhile to prove this result. So let's take a look at it. We're going to define a function, let's call it y of t, as a linear combination of these y1 and y2 functions, which we were told are solutions of this equation. Now, to show that this combination is a solution, we need to find our first two derivatives so that we can substitute into the differential equation. So if I look at my first derivative, y prime, well, just differentiating term by term, I have c1 times y1 prime plus c2 times y2 prime. And my second derivative, y double prime, would be c1 y1 double prime plus c2 times y2 double prime. So let's take these expressions and substitute into our differential equation. That is y double prime plus p of t times y prime plus q of t times y is equal to 0. So substituting these expressions in, we found y double prime was c1 y1 double prime plus c2 y2 double prime. Then we're adding p of t times y prime, which was c1 y1 prime plus c2 y2 prime, plus q of t times y, which was c1 y1 plus c2 y2. And we want to know if this is going to equal 0. So if we distribute and we group like terms, let's say that we group everything involving y1 or its derivatives together, and then we group everything involving y2 and its derivatives together, let's see what we have. So grouping the y1 terms, I notice that everything involving y1 is multiplied by a constant c1. So if I factor out a c1 from all of those terms, I am left with y1 double prime plus p of t times y1 prime plus q of t times y1 And then if I group all of my y2 terms together, I see that all of them are multiplied by the common constant c2. So if I factor out a c2 from those terms, I'm left with y2 double prime plus p of t times y2 prime plus q of t times y2. And I want to know if that's equal to 0. Now here we were told that y1 and y2 were solutions of this differential equation. So if I substitute y1 and y2 along with its derivatives into that equation, they make it equal to 0. But notice that these two expressions that I have inside of the square brackets, well, they're exactly that differential equation with y1 and y2 substituted in. So since y1 and y2 are solutions, both of these expressions in brackets are just 0. So I have c1 times 0 plus c2 times 0 is indeed equal to 0. So what I have shown is that my linear combination c1y1 plus c2y2 is also a solution of this homogeneous second-order linear equation. So what this superposition principle tells us is that if we have two solutions, y1 and y2, of a second-order homogeneous linear equation, then we can find infinitely many solutions by taking a general linear combination of the two solutions that we found, y1 and y2. Or in other words, any linear combination of these two solutions, y1 and y2, is also a solution. So if we can find two solutions, we can find infinitely many. Now, the next question becomes whether this general linear combination, so this expression that I've just written out, would include all solutions of my differential equation, or whether there may be other solutions of a different form. So we're curious if whether we find, or when we find two solutions, if a linear combination of those two solutions gives us every possible solution. Now, the answer to that question is going to come from something that we call the Wronskian of a set of solutions. So let's start by defining our Wronskian as follows. If y1 and y2 are two solutions of the differential equation y double prime plus p of t y prime plus q of t y equals 0, so this homogeneous second-order linear equation, then we would define the Wronskian of those solutions as follows. So first, let's start with the notation. The Wronskian is usually denoted as capital W, which would be a function of t, if t is our independent variable. Or we could denote it as W of y1 and y2. This Wronskian is going to depend on our two solutions that we're finding. And the way that it is defined is as the determinant of a 2x2 matrix, where the first row of this matrix consists of our solutions, y1 and y2. We put in the first row, and our second row of this matrix would be the derivatives of those functions, y1 prime and y2 prime. And then, of course, to find the determinant of a 2 by 2 matrix, well, we take the product of our diagonal entries, y1 times y2 prime, and we subtract the product of our off-diagonal entries, y2 times y1 prime. So this determinant, which depends on y1 and y2, which are functions of t, is what we define as the Wronskian of those two solutions. So before we see how the Wronskian tells us about whether or not a linear combination of two solutions forms every solution, let's just get a little practice of working with Wronskians. So in this next example, we are asked to find the Wronskian for the given pair of functions. And in part A of this example, we have y1 and y2 are two exponentials, e to the 2t and e to the negative 4t. So let's find the Wronskian. W, which would depend on y1 and y2, which are functions of t. And to find this Wronskian, we're taking the determinant of the 2 by 2 matrix, where our first row would be the functions y1, which is e to the 2t, and y2, which is e to the negative 4t. And our second row would be the derivatives of these functions. So here our derivatives would be 2e to the 2t and negative 4e to the negative 4t. So now taking this determinant, we multiply our diagonal entries. So we have a constant negative 4, then e to the 2t times e to the negative 4t gives us e raised to the negative 2t power. We just add those exponents. And then we subtract what we get by multiplying the off-diagonal entries, which would be 2e to the negative 2t. And so combining these terms, we have a total of negative 6e to the negative 2t power. So this would be the Wronskian of those two functions. Let's look at another one. In part B, we have y1 and y2 are the cosine and sine functions. So to calculate our Wronskian of y1 and y2, we take the determinant of the 2 by 2 matrix, where our first row would be these two functions, cosine of t and sine of t. And our second row would be the derivatives. So the derivative of cosine is negative sine, and the derivative of sine t would be cosine t. So when we multiply our diagonal entries, we have cosine t times cosine t, or cosine squared t. And then we subtract for the off diagonals, we have sine t times negative sine t. So we're subtracting a negative sine squared, or that's the same as adding sine squared t. And then we know everybody's favorite trig identity, the sum of sine and cosine squared of the same angle is just 1. So we can simplify our Wronskian down to 1 here. And then for the last part, part C, we have y1 and y2, which are functions of x instead of t here, x and x times e to the x. So our Wronskian for these two functions, y1 and y2, which are now functions of x instead of t, is calculated the same way. We take the determinant of the 2 by 2 matrix, where our first row would be the functions x and x times e to the x. And our second row would be the derivatives. So the derivative of x gives us 1. For the x times e to the x function, we need the product rule for our derivative. So we would have 1 e to the x plus x times the derivative of e to the x is e to the x. And so taking our determinant, we have, for the product of the diagonal entries, x times e to the x plus x squared times e to the x. And then we're subtracting the product of the off-diagonal entries. So 1 times x e to the x. And then, of course, we can see that a factor of x times e to the x cancels, and we are left with x squared times e to the x. So here we have defined our Wronskian for a set of two functions, and we've looked at some examples of calculating this Wronskian. So now let's see what this Wronskian tells us. Why is this Wronskian thing important for differential equations? So here we have another theorem. This is theorem 3.2.4 from your textbook, which says the following. If we suppose that y1 and y2 are two solutions of a second-order linear homogeneous equation, y double prime plus p of t y prime plus q of t times y, I should have a y there, equals 0, then the family of solutions defined by y of t equals c1 times y1 plus c2 times y2 with arbitrary coefficients c1 and c2 includes every solution of that differential equation if and only if there is some point t naught where the Wronskian of those two solutions is non-zero. So in short, what this theorem says is that if and only if our Wronskian of two solutions, y1 and y2, is not everywhere 0, that is, it's not always equal to 0, then every solution of the differential equation can be written as a linear combination c1 times y1 plus c2 times y2 for some constants c1 and c2. And in this case, that we have found two solutions whose Wronskian is not always 0, then y1 and y2 are said to form a fundamental set of solutions for that differential equation. So this theorem that involves, this theorem tells us that the Wronskian is very important when we consider the general solution of a second-order homogeneous linear equation. If we are able to find two solutions of our equation and their Wronskian is non-zero, then the most general solution is a linear combination of those two solutions that we found. So this kind of justifies what we were doing in the previous section, 3.1, why our general solution was a linear combination of those two exponential functions. If we look back at the previous example for just a moment, we saw here that if we had two exponential functions with different exponents, say 2t and negative 4t, so maybe we got these by looking at a characteristic equation with two distinct real roots, 2 and negative 4, we see that our Wronskian was not equal to 0. So those two functions form a fundamental set of solutions, and therefore our general solution of that equation could be a linear combination of those two exponentials, like what we were doing in section 3.1. So we finally justified why we could take our general solution in that way. So now that we have seen what the Wronskian tells us about whether or not a set of solutions forms a fundamental set, let's look at an example making use of this. In this next example, we are told to show that y1, which is given by the square root of t, and y2, which is 1 over t, form a fundamental set of solutions of this given differential equation. So the first thing that I need to do to show that these functions form a fundamental set of solutions is show that they are actually solutions of this equation. I need to find the first two derivatives of these functions and plug them into the differential equation to make sure it's satisfied. So let's look at the first function, y1. Here, y1 is the square root of t, or if you prefer, t to the 1/2 power. So our first derivative, y1 prime, would be 1/2 t to the negative 1/2, or 1 over 2 times the square root of t. And our second derivative, y1 double prime, would be negative 1/4 t to the negative 3/2, or negative 1 over 4t to the 3/2. So if we substitute these expressions into our differential equation, let's see if it's satisfied. We're looking at 2t squared times y double prime, which was negative 1/4 t to the negative 3/2 power, plus 3t times y prime, which was 1/2 t to the minus 1/2, minus y, which was just t to the 1/2 power. And we want to see whether this is equal to 0 or not. So let's simplify this a little bit. Grouping our first two terms, we have a constant of minus 1/2 t squared times t to the negative 3/2 gives us t to the 1/2. We just add those exponents. Plus, for the middle term, we have a constant of 3/2 t to the first times t to the negative 1/2 gives us t to the 1/2 if, again, we add our powers. And then minus a 1 times t to the 1/2 power. So when we sum these terms, we see that we do indeed get 0. So we have shown that y1, which was the square root of t, is a solution of this differential equation. Now let's do the same thing for y2. If y2 is 1 over t, or t to the negative 1 power, then our first derivative, y2 prime, is negative t to the negative 2. And the second derivative would be positive 2 t to the negative 3rd. And so now let's take these expressions and substitute them into our equation. We're looking at 2t squared times y double prime, which was 2t to the negative 3rd, plus 3t times y prime, which was negative t to the negative 2, minus y, which is t to the negative 1st power, and we want to see if this is equal to 0. So multiplying those first terms, we have 4t to the negative 1. For the second two terms, we have minus 3t to the negative 1, and then minus t to the negative 1 on the end, which does indeed give us 0. So we have also shown that y2 of t, which is 1 over t, is a solution. So these two functions do indeed solve our differential equation. The last thing that we need to show is that they form a fundamental set of solutions. So we want to show that the Wronskian of these two functions is not 0. So for the last part of this, let's calculate the Wronskian of y1 and y2, which are functions of t. We're taking the determinant of the 2 by 2 matrix, where our first row would be the solutions, square root of t, or t to the 1/2 power, and 1 over t, or t to the negative first. And then our second row would be the derivatives, 1/2 t to the negative 1/2 power, and negative t to the negative 2 power. So taking our determinant for the product of the diagonals, we get negative t to the negative 3/2 minus, for the product of the off diagonals, we have 1/2 t to the negative 3/2. And so summing them gives us negative 3/2 t raised to the negative 3/2 power, which is certainly not equal to 0. So since we have shown that these two functions are solutions and their Wronskian is not 0, we can state that y1 and y2 form a fundamental set of solutions.